Perfect. All right. Welcome, folks. My name is Ashwin. I think I haven't met some of you, though I do see a few familiar faces. I've been an instructor with Terra for a couple of years now. I'm currently instructing Okapi Group 1. I can see a few people from Group 1 here, also instructing the Pangolin cohort. So like I said, I've been instructing for a couple of years, and the Enroad simulator is one of the things that is very close to my heart. I enjoy playing with it myself. And today, I hope I'll be able to show you what the power of the simulator is, and maybe you'll go away with some insights about how to use it. So that's the goal for today. Before we begin, like I said, a few new faces around, a few familiar faces. So if you don't mind, just go to chat and let me know where you're joining us from. I am joining from Goa in India, the west coast of the country. I'd love to know where you're all from. Okay, New Jersey, Denver, Las Vegas, Rhode Island. Okay, Melbourne, Seattle, and Delhi. Okay, so we have a nice small group today. We might get more people join in, but I like this. Hopefully, we'll get a lot more interaction going this way. Folks, if you're able to switch your cameras on, I'd love to see your faces. It's really dreary talking to black rectangles on the screen. So if you can, please do. If you can't, I understand. Don't worry about it. Okay, so today we're going to be talking about the En-ROAD simulator. It's a very powerful tool. And you're well about two-thirds of the way through the LFA, through the course. So you've been already thinking about solutions and what solutions might be important in terms of uh, meeting our climate goals. So yeah, so I'm going to show you the simulator in just a moment. But even before I show you the simulator, I want to hear a little bit more from you. Maybe use the chat and let me know which solution that you've come across so far, either in the course or in the media, or you heard from somebody. It doesn't matter where you heard it from or where you found it, but which solution do you feel most optimistic about? Which solution do you feel we should double down on? And it's going to kind of take us a long way towards meeting our climate goals. So just go ahead and put that one solution that you really believe in into chat. Energy efficiency, okay, great. Electrify everything, great. Agriculture, okay. What else? Clean energy, yeah. Solar, perfect. Electrify everything, yeah. Solar again, okay. So it looks like electrify everything, energy efficiency, solar, clean energy, those are the themes, and agriculture. So while we're looking at the simulator, we'll try playing around with some of the solutions and see where they get us. Yep. So let me get my screen share up and I will show you what the simulator looks like and also how to use it. Any point in the during the session, if you have questions, just raise your hand and I'd be happy to come to you whenever I can. Yep. So this is maybe for some of you, your first look at the En-ROAD simulator. There's a whole bunch of things on this. Don't worry about it. I'm going to walk you through each one of these in a little bit of detail. So let's start with that. There's a couple of graphs on the top, and then there's this number on the right. So let me start with that number. This number, 3.3, is the temperature increase that we are currently on a path to achieve by the end of the century. So given how things are, given what policies are in place, it's a plausible scenario that we might reach 3.3 degrees of warming, 3.3 centigrade degrees of warming by the end of the century. Now, would someone like to remind us all about the goals of the Paris Agreement? What would we like this number to look like before the end of the century? Yep, 1.5. So the Paris Agreement has exactly, Sam. It says we definitely need to be below 2, and ideally, or preferably, we would love to stay within 1.5. So today, when we play with the simulator a little bit, that's what we'll kind of keep as our goal. We definitely want to get this number below 2, but if we can keep it below 1.5, I think that's great. That's brilliant. Yeah. So that's this number. Now, how does global warming happen? Well, it happens because of greenhouse gas emissions, and this graph is projecting into the future what our greenhouse gas emissions might look like every year, right? So there's time on this horizontal axis, and there's the number of gigatons of CO2 equivalent that we might emit every year on the vertical axis. So you can see but we are in 2020, we finished 2024, we were at around 59 gigatons. That looks like it's going to grow a little bit and plateau somewhere in the region of 70 or thereabouts. Yep. So that's what is currently projected as the most plausible scenario. Now, where do our emissions come from? So the biggest area where our emissions come from today is our energy use. And you've learned this in the energy classes that about 3/4 of our GHG emissions come because of our energy use, right? So this graph shows us our various sources of energy and how much of each source do we end up using in a given year, right? So we have coal down here at the bottom, and you'll notice that coal has kind of flattened out for now, but it kind of looks like it's going to increase a little bit towards the end of the century. We have oil up here as well. And again, oil, there's a good solid wedge and doesn't look like it's going to reduce by much by the end of the century. Same with natural gas as well. In fact, looks like natural gas might even end up increasing a little bit towards the end of the century. Again, all of these are plausible scenarios based on what is out there right now. So where does all the data for this come from? The En-ROAD simulator, it's built by a company called Climate Interactive. It's a nonprofit in conjunction with MIT, and they use the latest available science. So they use data from the IPCC, the IEA, the World Bank, and similar other such multilateral institutions and research bodies to inform their research. And they do multiple releases every year to make sure all of this stays current. Right. So according to them, according to the data used by the makers of this tool, we are going to see a slight increase in terms of how much fossil fuel we are going to use every year, right through to the end of the century. Now, the good part here is this green wedge, which is renewables. You can clearly see that increasing a fair bit through the rest of the century as well, and which is great, which is what we want a lot more of. Up here is bioenergy, and again, not a lot of growth in that, but kind of remains pretty much at whatever amount we're currently using. There's nuclear, which you can barely see. It's a small amount. It's projected to grow a little bit, but again, not by a lot. There's another one here called New Zero, and you won't see this on the chart yet, and I'll explain why in a moment. But these are our primary sources of energy, and we can clearly see at a high level that our energy use continues to grow right up to the end of the century and beyond. And as a result, greenhouse gas emissions continue to grow almost till the end of the century. And also, this is the resultant temperature increase that we might see. So you can see kind of a cause and effect relationship here, right? Because of our energy use, we have these greenhouse gas emissions, and because of the greenhouse gas emissions, we have this temperature increase. Yeah. Now, of course, our energy use is not the only way in which we emit greenhouse gases. There is land use, agriculture, and a whole host of other things that also contribute. But this is the biggest source. This accounts for 3/4 of our emissions. Yep. So that's the top panel, which we just went through. Now, how do we, we said our goal was to get this number down to below 2 and ideally below 1.5. How do we make that happen? All these sliders that you're seeing down here are levers for us to pull, and in doing so, try to get that temperature down to below 2. This first set of levers here on the left is all about energy supply, right? Where does our energy come from? There is coal, oil, natural gas, which is our traditional fossil fuels. There is bioenergy, nuclear, renewables, and then there's this something here called new zero carbon. Again, we'll come to that in a moment. So how does each lever work? Moving a lever to the right incentivizes something, right? Makes it easier to implement that, incentivizes it, kind of pushes for it. Moving a lever to the left impedes it or creates obstacles in promoting it, right? Or disincentivizes it in some way. Now, this tool is agnostic to what policy mechanisms you might use to incentivize or disincentivize something. So they don't recommend or push for any particular way in which to achieve this. They just say that if you've had a policy to incentivize or disincentivize a particular energy source, what might be the impact on temperature? So this is all about energy supply. New zero carbon Imagine there is a new source of new source of energy, which is as of today in the lab, and which we might expect to see coming online maybe in the next couple of decades, at some point before the end of the century. And there are examples of such technologies that are in the lab right now, which we hope might scale up in time. An example is nuclear fusion. Our nuclear energy right now comes from nuclear fission, but there are hopes that we might be able to make a breakthrough on nuclear fusion. And if we do, that might come online at some point in the century. And that's an example of another zero carbon energy source that we might be able to bring online at some point. So again, this slider is agnostic to which technology comes online. We're just saying, what if there were a new zero carbon energy source that we are able to bring online in the future? Yeah. So first panel on the left is all about energy supply. The middle section here is about demand for energy. How do we use the energy that we get from the left here? So transport is one major area. Then there's building and industry, and in both there are two sliders. One is to increase or decrease efficiency with which we use our energy, and then there is electrification. And we've learned a little bit about both of these things, so I won't spend too much time talking about. So there's transport, there's buildings and industry, and those are the, again, biggest ways in which we use energy at this point. Yeah. Down here, you'll see growth, and growth comes in two ways, either population growth or degrowth, and economic growth or degrowth. So number of humans on Earth increasing or decreasing, and the GDP per capita increasing or decreasing, right? So those are, again, two levers that we can use. And this is something you might have discussed in your labs, that economic growth, for example, there are proponents of green growth who say we need to grow faster in some sense, but while at the same time we reduce our GHG emissions and reduce global warming. There are others who say we need to degrow. We need to actually reduce the amount of growth we're seeing across the world, and that will lead us to lower this warming number. So again, all of this completely up to us, which levers to pull and by how much. The panel on the right, so the first two panels are talking mostly about our energy use. The one here on the left, on the right, is other sources of greenhouse gas emissions. So, for example, some of us are fairly gung ho about carbon dioxide removal, either through nature-based means or technological means. So again, we can play around with those and see how that impacts net emissions. There are other sources of GHGs, like agriculture is one, waste and leakage through our entire supply chain of fossil fuels is another. Deforestation is a major cause of GHGs. So all of these are levers that we can pull. Yep. Okay. So this was just just an introduction to what we can play around with to impact this number here on the right. And I'm going to pull the first lever in a moment, but let's see what Priyanka wants to say. Priyanka, go ahead.
Hi, sorry, just a quick question. In the levers, why does the status quo look at different stages for each of the levers?
Yeah. So depending on what is the most likely outcome we may want, or most likely usage of that lever, like for example, for renewables, the most likely answer is going to be to increase their use, not decrease, right? For us to be able to meet this goal. In the same way, for coal, we most likely wouldn't want to increase our coal supply. We want to decrease it. So depending on what's the most likely thing that you might want to play around with for that particular lever, they've kind of put it in a particular place. But that doesn't mean it's kind of set in stone. Let me show you. If you click on these three dots up here, you can actually play around with the details and even exceed, how much that lever can be pulled or how much impact that lever might have. So even though the lever is placed in a certain way, doesn't mean it's set in stone. You can change that around, or you can change the effectiveness of that lever by going into this three dot menu. Kaushik, go ahead.
Yeah, so I just wanted to comment on the carbon price. I played around with this. Carbon price, I think, plays a big role. If you move it, I've seen the temperature change is considerable. And given that CBAM and a lot of other initiatives coming up, I think carbon price is an important.
Absolutely. And again, I mean, my goal here is to not promote or dissuade you from using one of these levers. I'm going to give you full control. In a few minutes, you're going to go into breakouts and play around with all of these levers. And I actually want you to play around with carbon price when you go into those breakouts. there are pros and cons of a carbon price, and we'll probably come back to the main room and discuss some of them. But before I send you off into breakouts, I want to show you, what happens when you pull a particular lever, right? For example, clean energy was one of the things that some of us were pretty optimistic about. So I'm going to pull this lever, which incentivizes renewables, which is clean energy, all the way to the right. Yep. So I'm going to pull this lever all the way to the right. What I want to ask you is, before I pull this lever, how much of an impact do you think it might have on the temperature? So in degree C, how much impact would we have on warming if I pull this lever for renewables all the way to the right? What do you folks think? 1 degree? Okay. A couple of people saying 1. Any other numbers coming in? 0.1, 0.5, okay. 1.5, okay. 0.5, okay. So we've got a range in here, starting with 0.1 going all the way to 1.5. So how about how about we pull that lever and see what happens? Yeah. So here goes. I'm going to pull this lever all the way to the right. How much did we see? 0.1. Now, for a lot of people, that's like, oh, just 0.1. I was like so optimistic about this particular solution, and it doesn't look like it's very impactful. So let's look a little bit under the hood and try and understand why this is happening. Why is in pulling renewables all the way to the right, which means we are highly subsidizing it, not result in a drastic decrease in warming? Now I'm going to replay this change. So it will kind of pull that lever 3 times just to show us what happens. Just watch the graph on the left, this graph, just watch it. Watch what happens to it as the lever gets pulled. Yeah. So what we're seeing here is, of course, the green wedge, which is renewables, that increases dramatically by a fair amount. And we also see the the 3 fossil fuels kind of getting pushed down a little bit. So they reduce all of them. But what happens to overall energy use? Pull it again. Overall energy use actually goes up. Now, why might that be happening? All we've done is we have subsidized renewables. So renewables will become cheaper. And that's what we want. Why is that pushing up overall energy use? So maybe let's look at a couple of other graphs and see why this is happening. So these are a few graphs, and En-ROADS has a bunch of graphs. I'm not going to show you all of them. You can play around with those in your own time. But okay, let's replay and see what happens. So in sources of energy, you're seeing the green line go up, which is renewables. You're seeing gas, oil, coal come down a little bit. But what are we seeing with cost of energy? We're seeing the cost of energy come down. Now you might have discussed this in lab. There's this thing called the Jevons paradox. When something gets cheaper, we start using more of it. So what we wanted was for renewables to come in and replace fossil fuels. What is actually happening is we are getting more renewables, but we are not really replacing fossil fuels. We are using fossil fuels and then adding renewables on top of that, which is why its temperature did not decrease by a whole lot. Is this making sense so far? Yeah, okay. We're going to try another lever before we go into breakouts. So let me pull all the levers back to where they were. What was another? So I think energy efficiency or electrification was another one where people were fairly optimistic about. So how about we pull the lever for electrification on transport? How much do you think will impact warming by? Can I get some numbers in chat? So electrification of transport, if we really, really push hard on that, 0.1. Okay, now we're getting realistic here. 0.3, 0.5, 0.3. That's a good point, Vishaka. It won't impact much unless we also increase renewables. So let's see how that plays out. So I'm going to pull this lever to the right. And now we know what to expect. We know that that's not going to improve the number by any big amount. Well, it did actually. So let me show you. It's too small to show up. So this number was 3.31. We pull it all the way to the right. It becomes 3.26. So half a degree So it did go down a little bit, but not by a big deal. And again, I'll replay this and you can watch this graph for a moment and see what happens. So we electrified a whole lot, and that increased renewables, but it also increased overall energy use again. Now, why did renewables increase, do you think? If we didn't incentivize renewables here, we just electrified transport. Why did renewables increase? Any guesses or answers? Why might that happen?
Demand increases.
Demand increases, yes. And the way in which we electrify our transport right now, I'm sorry, what I meant to say was that even as of today, if you look at cost of energy, and I'm going to show you those smaller graphs again, the cost of electricity as it stands, renewables is already the cheapest form of energy available to us. So if we increase demand, what Sam said was demand increases. So we increase demand, we want more energy. The cheapest ones are the ones that kind of come online the most, right? So which is a good thing, which is absolutely not a bad thing at all. So when we increased electrification, we started using more renewables. But what Vishaka said was that just this by itself won't have an impact. We also might need to incentivize renewables. So I'm going to pull, while electrification is pulled all the way to the right, I'm also going to pull the renewables all the way to the right, which is, I guess, what Vishaka you meant in your comment. So let me do that. Okay, came back down by a little bit more. So you remember this was 3.31 to begin with. Now it's at 3.16. So yeah, we're doing better, but still not good enough. And again, we're seeing renewables grow quite drastically, but we are also seeing our overall energy use go up further. And again, we have the same Jevons paradox playing here. So what does all of this mean so far? It means that just incentivizing renewables, incentivizing electrification by itself won't get us where we need to. And why is that? Because we are not replacing fossil fuels. We haven't done anything to control or reduce how much fossil fuel we use. So maybe the answer lies somewhere here. Maybe it lies with the carbon price. I don't know. I'm going to leave you to play around with this a little bit in breakouts. And when you come back, maybe we might have some discussion. Alexa said exactly that. We might need to disincentivize gas. So maybe that's the answer. So I'm going to put together a few breakouts. I'm going to send you into breakouts in a moment. Just a few comments before I send you on your way. Number one, one thing you may have noticed here is like pulling levers is easy, right? I mean, I'm just moving my mouse pointer about and moving things about, but actually implementing this is hard. And there are competing incentives. We have limited amount of political capital, limited amount of money trying to move all of these things. So in real life, there are constraints. The simulator might not impose them on us, but in real life, there are constraints. We can't just willy-nilly pull every lever that's available to us. We have to be conscious that there are constraints, and we can't indiscriminately use everything that's available to us. Yeah. So even though the simulator does not impose that constraint on us, I am proposing that we impose that constraint on ourselves, right? So when you go into breakouts, you're going to try to bring this temperature down to below 2 and ideally to below 1.5. I would say don't use more than, say, maybe 6 levers, right? And again, we're just trying to simulate in our minds the fact that there are constraints and we just can't use every single lever. Of course, I mean, if we move every lever to the right or to the left, depending on what lever, all the way, we are going to see drastic change. We are going to go below 1.5 for sure. So that's not in doubt at all. Yep. So that's number one. Try to use 6 or fewer levers and try to get us to 1.5. Yep. Sam, what did you have?
Sorry if I missed it. Did you explain what new zero carbon is?
Yep. So I'll talk about that for a moment again. New zero carbon is talking about an energy source, which is as of today in the lab somewhere. Somebody is working on it in a research lab somewhere. And we expect or hope that this might come online at some point in the future. And you can actually go in here and you can look, you can play around with, how long does it take to scale this up? What's the cost of energy coming from this source, and so on and so forth. Yeah. So right now we have new zero carbon energy available to us. If we pull that lever, zero carbon energy, a new source, will become available to us and get scaled up at some point, at some later point in this century. Yep. Does this make sense? Yeah. All right. So yeah, so some more comments on before I send you to breakouts. Use 6 or fewer levers if at all possible. When you come back, I'd love to hear from you a little bit. I'd love to hear your thought process on how you went about using all of these levers and getting us to our temperature goals. So please nominate someone who might want to come back to the main room and share with the rest of the folks. Also, once you're done building your scenario, you can go here to share your scenario and copy scenario link. So make sure you copy that link and have it handy so that when we come back to the main room, you can send me the link over chat and I can actually pull out your scenario and all of us can look at it. There's a question from Megan in chat asking if hydrogen is considered new zero carbon. It can be if the hydrogen is generated using zero carbon energy in the first place. Yeah, so not necessarily, but it could be a zero carbon energy source. All right, any last questions before I send you off? I should be able to give you about 20 minutes, maybe a couple minutes more if you need it. While in your breakouts, you might see me pop in for a minute or two. I just want to see how you're going, if you have any questions. If you're going okay, just ignore me. I'm just a fly on the wall. If you have questions, of course, happy to answer them. Kaushik?
This 6 lever thing is strict. I did play around earlier, but I used more than 6.
I would say try. I mean,
Okay.
we're just imposing it on ourselves, so it's not strict in that sense. I'm just saying try get to where you need to or when you want to by using 6 of your.
Got it.
Yep. Okay. So I'm putting those rooms together now, and I'll see you back in about 20 or 22 minutes, and I'll be in your rooms for a bit. Just see how they go. Yeah. All right. Have fun. Oh, I'm sorry. I did not give you a link to the simulator, so let me do that. You might have found it already, but let me give you a link. Yeah, there you go. And rooms are open. All right, how did that go? You can see a few smiles and an eye or two. Anyone want to just tell us, everyone else, your general impressions of how that exercise went? Go ahead, Tam.
I found it quite interesting when we, for example, were trying to pull the buildings and industry electrification lever. It was for us, I guess, quite a good conversation starter to understand why it wasn't making a difference. That's just an observation.
Absolutely, no, yeah. Yeah, I was just going to say, drop your scenarios in chat and we'll go and look at those in a moment. Alexa is saying that was very eye-opening. Yes, it is. And the more you play with it, the more insights you start getting. So maybe we'll get a chance to talk about a few. So how about we have scenarios from group 1 in chat. Which one should I open first, the realistic or the less realistic? Okay, I'll just pick
Realistic.
Let's start with realistic. Okay, I'm opening that up and let me share my screen and then you can walk us through your thought process there. Okay, over to you, group 1.
So with this one, we picked 6 levers. These are the levers we found were had the most impact on temperature. But then we moved them to a point where we thought was actually more realistic and achievable socially, politically, economically, all that fun stuff. And we found that it was very difficult to get to even 2 degrees if we are trying to be realistic with only 6 levers.
Okay, and how did you go about choosing what levers to put?
So we also chose one in each of these sections. So trying to make it like a broad-based approach. The playing around with sort of taxes on taxes or incentives on the sources of energy was interesting. In it moved, some moved the needle, some didn't, but what was clear was the carbon price moved the needle the most. But we agreed that we can't, a high carbon price just is not achievable, as we've seen in, well, sort of any country, that there's no country with like the appropriate or the correct price on carbon. And there's lots of countries like Australia where governments have been tossed out because they've tried to implement a carbon price. So that's why we went with medium instead of high. And then we chose, efficiency. We saw was seemed to have like quite an outsized impact. The discussion around buildings versus transport to us seemed easier to achieve energy efficiency, where buildings and industry less so. For example, cars get replaced more often than houses and buildings. And then growth, lessening growth is good, but no one can ever will buy into far less economic growth. And then sort of same approach for the other two.
Sounds great, and we'll come back to some of those themes in a moment. I'm also going to open up your other scenario, which was the less realistic one, and let's see what you had there. Okay, so here you've, I think, pulled more or less the same levers, but all the way. Is that accurate? I think more or less, maybe.
Yeah, more or less, actually. Yeah. That was an accident. We didn't mean to do that. I think Megan did this one separately, and then we played around with it.
Okay, no, that sounds great. I mean, there's a reason why this particular combination of levers gets you close to 1.5, and we will talk about those reasons in a minute as well. Anything else, group one? Anything else you would like to bring up, ask? Anything at all before we go to group two? No? Okay, so I'm going to open up the simulation for group two, and let's talk through that. So you've reached 2 degrees, which is great. Do you want to tell us how you got here?
Yeah, I think I can start, and then maybe Dan or Kaushik can add on to it. So we all agreed that for energy supply, the two levers that would make the most difference would be taxing coal, subsidizing renewables, and increasing carbon price. So because if you, like we saw in the simulation with you, Ashwin, if you just increase renewables, it's not going to really replace fossil fuels. And amongst the fossil fuels, since coal is the most harmful, we tax that. And we kept coal taxing at, maybe it's not very realistic, but we didn't push it all the way to the end. But for subsidizing renewables, we thought that's more realistic, so we pushed it all the way. And between transport and buildings industry would had a little bit more of an impact. And like Dan mentioned, it was surprising that electrification didn't have too much of an impact when we increased both efficiency and electrification. It didn't make too much of a difference. So we only increased the energy efficiency bit for buildings and industry. And then we were playing around with a lot of the other levels. We tried carbon dioxide removal, deforestation. We didn't touch population and economic growth because not sure how realistic that's going to be or how many proponents of that are there. So what we found most effective was agriculture, waste and leakage. And again, not sure how realistic it is, but we moved it all the way to the left. And in the end, I think that led to almost a 0.3 decrease, these two levels together. So that was our logic broadly.
Thank you for that. That was great. And you mentioned that you didn't touch population and economic growth because it's not realistic.
Mm.
But if you didn't impose that limit of 6 livers, I guess at some point you would have gotten to those as well, right?
Yeah, probably.
Yeah. So constraining ourselves to 6, again, this was just, you can go back to the simulator and try out, whatever combination you like, but restricting ourselves to 6 is just a reminder all the time to ourselves that there are constraints in the real world. But I feel like both groups, both breakout rooms, I think you did a great job keeping those constraints in mind all the while. Every lever that you pulled, you're thinking about, should I pull it all the way? Is this realistic? Can we get this done? Is it possible? Which is great. Many times I see, people are just pulling levers without thinking too much about them. And both rooms, you were very conscious about what you were doing. So thank you for that. So I'm gonna go back to a fresh En-ROADS window. Just in case, before I go to the fresh window, I wanted to show you a scenario. Again, this is very close to what one of your less realistic ones. So if I had just made it an exercise to get as close to 1.5 as possible while pulling only 6 levers, this combination kind of seems to get us closest. Still doesn't get us to 1.5, but almost there. Yeah, and again, we'll come back to why this particular combination seems to get us so close. Yeah, so we'll come to that as we discuss more. We have a small group today, so any questions, anything comes up while I'm speaking, please feel free to chip in, just unmute and speak. And we'll try to make it an open discussion. Kaushik, go ahead.
Yeah, I was just wondering about the electrification. Is this model up to date? Because I think general agreement is going to renewables and electrification and carbon dioxide removal. These 3 things should get us to 2 degrees. But
So
in
let's
this
try that,
simulation, we don't see that. Yeah.
Let's try it out. Let's try doing that. So let's electrify. And you'll notice when I pull both electrification levers to the right, our energy demand actually went up. Yeah. Now, the other thing you mentioned was we need to incentivize renewables. So let's incentivize renewables. Again, overall demand for energy went up, not down. Then you talked about could we then maybe pull
removal
carbon out. So yeah, let's do that. So let's maybe pull nature-based, and let's pull technological as well. Again, this is a thought experiment. So let's see what happens. And we're seeing a lot. But what we're not seeing is the 2 things actually. We're not seeing overall demand fall at any point of time. We're still continuing to grow our overall demand for energy. And these 3 wedges remain solid because our demand for energy has gone up to so high an extent that any amount of growth in renewables is not going to help us get this total amount of energy that we need, which means we continue to use.
Why is that happening? Why is the demand increasing?
Overall demand for electricity, because we've electrified everything. Now we need more electricity. And when we're electrifying everything, again, I'll show you the other graph. You're seeing that when we subsidized renewables, the cost goes almost down to 0. And even when it bounces back, it's still a very low price as compared to anything else. So we're getting very cheap electricity from renewables. So we are going to try scale that up as much as possible. And you're seeing that here, right? You're scaling up renewables as much as possible. But again, because of the Jevons paradox, because we're getting something cheaper, we're going to use more of it. So instead of overall demand for energy consumption, the black line is the baseline scenario and the blue line is growing even further. So we are going to continue to increase demand for electricity if we just electrify everything and move to renewables.
I see.
So what we also need to do in addition to all of these is control or set some way of reducing fossil fuel use, because that's not naturally happening. Yeah. So if you were to remove coal, then you'll start seeing the energy consumption line start going lower, and oil and natural. So again, this is a thought experiment, which is why I'm pulling them all the way. But the insight, at least, I am getting from this is electrification and renewables by itself is only one part of the answer. The other part of the answer is that we need to somehow disincentivize fossil fuels. Otherwise, we will use a lot of renewables, yes, but we will also continue to use a lot of fossil. Making sense so far?
What's the temperature now with this combination?
Let's go back and look at it. We're at 2.3, which is not too bad, actually, knowing how difficult it is to get to.
If you bump energy efficiency, Ashwin, then
Yeah.
do we get below 2?
Yeah, we can try it, but I want to talk about energy efficiency separately as well, and we'll do that in a moment. But yeah, you're right. We will get to 2 if we bump energy efficiency. Yeah. So let's think about why energy efficiency is that effective, and let's start from scratch. And yeah, so energy efficiency by itself is a fairly powerful lever. I mean, individual levers here, we've seen that the impact is not a lot, but if we pull energy efficiency just by itself, we see 0.3 degrees, pretty big. Why do you think this is happening?
You're using less
buildings-
energy to do the same things.
Exactly right. So if you look at these graphs, and I'll replay the change, look at energy consumption up on the left. So we're drastically impacting how much total energy we use, which by itself is very powerful. So, again, when we talk about different ways of achieving our climate goals, there are some pathways which don't talk about our use of energy, overall use of energy. And what's becoming more and more clear the more we use this tool is that that's no longer feasible. If we have to get to our climate goals, we have to figure out a way in which we use less energy to get the same benefit that we do today, which means we need to work a whole lot on energy efficiency. And again, on transport, again, I'll pull this back and pull the transport efficiency one. Although it is right, you'll see an impact, but a lot lower impact. And why don't I ask you, why do you think that is? Why do you think buildings and industry efficiency contributes a whole lot more than transport?
The heating and cooling, I think, for buildings and industry. Right?
Heating and cooling, yes, that is part of the answer, but there's another part to it.
The use of steel and cement.
Yes, so steel and cement are major uses of energy. So if you make them more efficient, yes, that's another part of the answer. But there is something else in there as well.
Is that buildings are already like significantly less efficient than transportation is?
That too, and there's a reason for why. Buildings stay around forever. I mean, by forever, I mean like half a century or even longer sometimes. Cars, maybe 10 years, maybe 15 years, you're going to trade up to a newer car. I mean, the old car is going to get scrapped and you're going to have a new car come. So any technological improvements in efficiency, they cycle into cars and vehicles much faster. Whereas in buildings, even if the newest buildings that are built today are really, really efficient, much of our building stock is like decades old, even like half a century old. Right. So we are still using energy in the same way as we used to half a century ago when we talk about buildings and impact. This fact is called the jargony term for this is capital stock turnover delay. What it means is that we have a bunch of investments already made, which are already in place, and it takes a long time for us to retire those and get new ones online. This is also apparent in other places, like for example, let me show you something else. How about, let's say where else might we see it? Economic growth. Let's say we say we are going to degrow. Yeah, or another place to see it is actually this one, new zero carbon. We've not really talked about new zero carbon. So let's say nuclear fusion becomes a real possibility in maybe in a few years' time, and we're able to scale that up really, really fast. So you see that it has an impact, but not really a lot, only 0.1 degrees by itself. And why is that happening? Let's look at those other graphs, and I'll replay the change, and we'll start seeing why. Anybody seeing why this is happening?
It's replacing renewables.
That's one part of the answer. Yes, absolutely. And that's because we incentivized it so much, the cost of new zero carbon is lower than even cost of renewables. So we are going to, this is called squeezing the balloon. If we squeeze it on one side, it bulges out in another direction. So yeah, so if we incentivize it to that extent without touching the price of coal, oil, natural gas, we are going to see it crowd out even renewables. But that's only part of the answer. Let me go back to the main view. You'll see the new zero carbon energy, which has come online. We only see it come online at scale decades from now. Like this is like 4 decades out, 3 decades out. And that is another example of capital stock turnover delays. We already have power plants using coal and natural gas, which are already in place, which are already operating at full capacity. Retiring those takes time because there is an investment sitting there, and this is called standard investments, right? Nobody wants to retire an investment before it has kind of paid back its entire due. Yeah, so nobody wants to leave money on the table and retire like coal plants, for example. So that's another example of capital stock turnover delay. So we talked so far about why electrification on its own is not good enough. We still need to do something about where our energy comes from. The other interesting thing I want to talk about was carbon price. But before I go there, I'm just going to check the chat to see what if there's any questions. Capital stock turnover delay, yeah, absolutely. Okay, let's talk about carbon price. And I think both breakout rooms captured this very well, that it's a very difficult political tool to use, political and economic tool to use, because it's really hard to get enacted. But let's imagine a scenario where we are able to get a high carbon price, a really high carbon price. So let's pull it all the way to the right. Yeah, in terms of one single lever which is able to get us close to our goals, this is the most powerful lever by far. Why do you think that is? I'll replay this and make
Economics.
Yeah, okay, tell me more.
Yeah, it'll encourage less carbon intensive products. So it'll kind of spur innovation across all industries to find alternates of low carbon intensity products.
Yes, that's the hope. So I'll replay the change and you can see what's happening on those various different graphs. And that will hopefully answer why it's so impactful.
The cost of energy will go up and people will use less of it because it doesn't make business sense.
Exactly. I think the biggest reason why a carbon price is so impactful is you can see the spike in the cost of energy. And because energy becomes so expensive, we're going to start using less of it. And why does this, it grows, but there's this dip here because, our fossil fuels are going to ramp down because it's just too expensive to produce energy by using fossil fuels. And renewables are going to ramp up, but renewables are going to take time to ramp up, right? You can't overnight suddenly bring, you can't overnight suddenly replace all our fossil fuel generation by renewables. So it's going to take us time to build up supply of renewables. So in the meantime, our energy consumption is going to drop, stay low for some time, and then start to grow as renewables kind of scales up, But the reason why
it
it's so
doesn't
impactful. Yeah, go ahead.
Sorry. No.
So,
but it doesn't talk about economic output, right? If I suddenly increase carbon price, what does it mean for GDP and overall
that's a great
economic growth,
question.
right?
Let's try look at economic growth here. So what is currently happening is economic growth by itself is not being impacted a whole lot, even though, let me replay that and show you what happens, right? It just goes up a little bit. There's another set of graphs. Actually, let me try show you those. Yeah. Sorry, hang on. So there is this notion of Kaya graphs, and I'll pull this lever back and explain what the Kaya graphs are all about before we start playing around with it. Again, very insightful. What the Kaya graphs are trying to show us is that our total emissions finally from our use of energy is a product or multiplication of these 4 factors. Yeah, and again, the mathematically inclined will see this as a multiplication, but we can just, even if you're not mathematically inclined, you can just think that total emissions from energy are controlled by these 4 factors. What are those 4 factors? One is the population, the number of human beings on Earth. GDP per capita, so the amount of global output per person, right? So how many people are there and how much consumption happens per person, energy intensity of that consumption, right? So how much do you consume, each person, how much does that person consume, and how much energy does it take to produce goods and services for that consumption, and then how much carbon or CO2 is emitted in producing the energy which is required for producing those goods and services that each person consumes. So again, logically, if you think about it, if you multiply all these four out, you will get CO2 emissions from energy. And you can use these graphs to you look at a whole host of things. Like, for example, what if I will pull population down drastically? You'll see none of the other none of the other graphs are impacted. Only the population graph kind of bends downwards, and that ends up giving us a decrease in emissions. Even here, you're seeing this delay effect. So this is not capital stock, but you're seeing the delay that any drop in population takes still maybe 2 decades or 3 decades to come about, because any policy you enact today is only going to impact future generations, right? So there is that inherent delay in there. I'll show you another one. How about we agree on degrowth and say we pull economic growth down sharply? Again, you'll see population and these other two graphs, they stay exactly how they were, but the GDP per capita, so the amount of consumption per person on Earth, goes down, which results in a decrease in energy use. So these Kaya graphs are, again, a powerful idea for us to kind of play around with and try and understand what are the different factors which govern our emissions from energy and how can we reduce those. I'm going to pause for a minute and ask if there are any questions. We still have about 10 minutes to go. I have 1 or 2 points I wanted to cover, but maybe you can take a couple of minutes to see if there are any questions. No? Okay. So just kind of coming back to what insights we get out of this, right? And I'm going to summarize that in a moment. But before we go there, I just want us all to maybe take 1 minute of silence. Think about that world, and you've written your 2040 visions, right? Think about that world that you want to live in, right? We want all of us to live in a couple of decades' time. Just imagine that world for a minute, and think about, after what you've seen today, think about how important it is for us, for you, and for every one of us that we get to that vision, that we get to that world. So I'm going to give you all a minute to think about that before we come back and summarize our insights. So 1 minute of silence. All right, thank you for that. And I hope what you've seen so far in the session today and those 2040 visions, they become all more important to you. So I'm going to spend the next few minutes, maybe 4 or 5 minutes, just kind of summarizing what insights you might have gotten from this, and please add to those if there's something that I don't cover. I wanted to start with showing you this one, right? This scenario is the one with only 6 levers pulled all the way, of course, but getting as close to 1.5 is possible. And I wanted to, kind of talk about why this particular combination of levers gives us that impact. So the one thing we have to realize is that we need to make impacts in complementary directions. Doing too many things which kind of achieve the same thing won't help us. We need to go in different directions and make impact in different directions, different areas, and different ways for us to reach our goals. I'll give an example. Just this one lever of carbon price is equivalent to pulling the renewables lever all the way to the right, coal, oil, natural gas all the way to the left, and also some parts of electrification and efficiency. Just this one lever. What this is telling us is that putting a high price on carbon will take care of everything that we need to do on the supply side. Yeah. So we could either pull these levers individually, or we could pull the carbon price lever. The result is going to be pretty much the same. It's going to decarbonize our energy supply. Yeah. Energy efficiency is going to control how much energy we use or reduce how much energy we use overall. So this is kind of greening our supply. This is making us use less energy. So by themselves, these two levers acting in different directions are going to take care of our energy use. Now, these other levers up here, let's talk about carbon dioxide removal. I was one of those people who used to oppose carbon dioxide removal, saying, if we do technological carbon dioxide removal by, in particular, this will be like, we'll use it like a get out of jail free card. We'll just say, oh, we're going to just suck carbon out of the atmosphere and we don't need to do anything else, right? Humanity will use it as a get out of jail free card, which is why I was like, no, this is not part of the solution for me. I have realized that no longer is a viable scenario anymore. We have historically, over the last couple of centuries, put so much carbon into the atmosphere that just reducing current emissions or future emissions by itself will not get us to our eventual goals. So for us to achieve those goals, we need to be able to pull some of that historical carbon that we put out there into the atmosphere back out. And again, there are nature-based and technological means available to us, and we probably need to use them both. So again, this is an example of working in a different direction. So the first two levers worked on energy. These levers worked on pulling carbon, which is already out there historically, pulling that out. So again, different direction. Agricultural emissions again, and none of these levers so far have touched waste and leakage in agriculture. The bulk of the emissions from agriculture come from beef, methane emissions from cattle and beef, and growing of rice, methane emissions from rice. So again, these are not touched by any of these other levers. This lever is doing something in a different direction. Waste and leakage, again, a lot of wastage happens in supply chains in our fossil fuel industry. So again, this is acting in a different direction. Main kind of, just to summarize, we need to act in different directions, complementary directions, not just looking at energy or not just looking at agriculture or removal, all of them. Yeah. Now, a lot of the time, I've seen folks come into this session with certain ideas or certain mental models of what they believe in to be really powerful solutions. Like when you came in, some of you said solar or clean energy is really the thing to go after. Somebody else said agriculture, and so on and so forth. And you're all right. But sometimes it happens that if we just end this session right now, there's a chance some of you might go away thinking, I thought this was an answer and it's not part of the solution at all. Well, that's not true. We've seen that it is very much part of the solution. The only thing to add on to that is that it's not a single silver bullet solution. By itself, that solution that you really deeply believe in may not be enough. We need a lot of those different solutions to come together and act. And finally, again, one outcome of this session sometimes is that people go away thinking, this is too hard. It's just too much. I don't think this is possible. There's so many things in so many different areas and sectors that we need to do. I don't think we're going to be able to get this done. Well, we already knew this was going to be hard even before we came to this session, so that didn't change. I hope what changed is that this showed you this is still possible, right? Using science and math, I hope this demonstrated to you that getting to 1.5 or close to 1.5 is still feasible. It's still possible. Of course, we'll have to do a lot of work, and it's going to be hard, but it's not impossible. It's still very much in our hands. And I hope that and your 2040 vision that we just talked about a minute ago give you enough inspiration to work harder and try harder to get us there. I'm going to come to questions in a moment, but I hope you go away from this session feeling energized, feeling optimistic, knowing that this is possible, and knowing that the solution that you most believe in is part of the big picture. It's not a silver bullet, but we are going to need a lot of seeds to grow our garden. So I hope you go away with those insights in mind. All right, we just have a couple of minutes to go. I'm happy to stay back longer if there are more questions, but Kaushik, what did you have?
Yeah, fantastic way to present this. Thank you for doing that. I was just wondering, the 6 levers, is it some scientific reasoning behind that, or is something as like a more of mental exercise? Because I use a lot more and seems like a little easier.
No, it's a bit of both actually. It's there is science behind why this combination works so well, and like I said before, it's because it acts in different directions, right? There's the notion of complementarity where you're doing things in different directions, which gets us there.
But there's some challenges, right? You know, we put the technological carbon dioxide removal all the way the highest level, but there may not be technologies out there which can do that, right?
Absolutely. And that's why this is, I'm still right now, this is at a level of a thought experiment, and we try to do it in 6. The eventual answer, again, if you ask me, if we talk about theories of change in labs, so the eventual theory of change that I have is we're going to have to pull probably every single lever here, but not to the extreme. We're going to pull all of these levers to some extent and come up with some combination that will eventually get us to our goals. This is just to show us that it's possible, and we are going to have to work in many different areas and many different solutions to get us there.
I'll share mine in the chat. I used everything except the population growth and economic growth. That got me to, is the right one? Got me to 2 degrees.
Yeah. So I think the eventual picture is probably going to look something like this. Maybe addition of a little bit of degrowth or something like that. I don't know. But yeah, I think this also illustrates the same point that we're going to have many different solutions in many different areas for us to reach our goals. Okay, I'm going to stop sharing now. Any last questions before we finish up? No. Okay. Thank you folks for engaging. Thank you for coming. And I think you did a great job in your breakout rooms as well. I hope this was insightful, and I hope to see you around. Thank you.
Thank you all. Bye-bye.
Thank you. Have a good night.